Good morning. Any questions or comments? I want to work out some details about Hofstadler model. First, let me remind you tight binding method. Let's focus on 2D, and I'll start with B is equal to 0, but I'll generalize it later. So Hamiltonian is, there are different ways of writing this. My preference is something like that. You sum over all sides, CR dagger CR plus X plus CR dagger CR plus Y plus Hermitian conjugate. So what this means is you need that these two terms with Hermitian conjugated. And here this means like we have like a square lattice, something like that. And this first term takes from here and hops you to here, and the second term takes you from here and hops you from there, and Hermitian conjugates does the reverse. And if this is R plus X, and I am taking lattice constant A to be 1, and this is also A to be 1. An alternative way to write the same Hamiltonian is minus T. Some people like this form, R plus X plus R. Actually, the other way, but it doesn't matter. Let me just write it like this. It's not actually important because there is also Hermitian conjugate there. So this is R plus Y vector plus Hermitian conjugate. And if you substitute in this Hamiltonian like a general ansatz, like a wave function of the form, like something like that. Let me use like a different R prime, psi R prime, and if you use like this, R prime R is delta R prime R. Like it's like a standard. You can also obtain this form. Let me just write the result: minus T psi R plus X plus psi R minus X plus psi. Actually, let me just copy. So this is Y, and this is Y is going to be equal to E times psi of R. But this is in the form of like a difference equation. And you can use Bloch theorem here. Like Bloch theorem is written in the form like psi of R is equal to some normalization, some k dependent form times e to the I k dot R. And this will immediately give you E is equal to minus 2t cosine kx plus cosine ky. So if I didn't take A is equal to 1, I would have like cosine kx times A here and cosine ky times A here. Good. Now let's turn on B. So let me just copy this first. So now B is non-zero, so we want to put a magnetic field on this lattice, and I have to choose a gauge, and let me just choose the lambda gauge, 0 Bx 0. And if you take the curl of A, we are going to find that B is equal to B times Z hat. So this is like in the positive direction. We don't need like a sign convenience sign here. And what we said was we were supposed to do was like Tij was replaced with Tij times exponential I e over h bar c, and we take the line integral from Ri to Rj, dr dot, let me put R prime if you want, A of R prime. So I think everybody remembers that, hopefully.
Why don't we choose minus dx?
You can also choose it, then magnetic field will be into the page. The one I choose here is like out of page. Nothing will change, right?
In non-gauge, before we choose.
Yeah. So we choose minus because it was more convenient. If you choose like this, everything we did would work out. Only difference would be like you had like we had like x minus xk squared. The only difference you would just find x plus xk. And since I had been like a little bit picky about this sign, I chose, and Gerwin Yang also chose there, but here it's not necessary. So that's it. So what we need to do is like, so there is only nearest neighbor hopping, still nearest neighbor. Then I only need to like, so these are called Peierls phases. I only need to calculate this for this hopping and this hopping. Then everything is done. First, let me focus on this hopping. This is going to be hopping from R to R plus X. And so I need to just calculate this dr dot A of R. And so this path is going along x direction, so this is going to be dx. And I need to pick up the x component of A, which is 0. So this is going to be 0. So from here, we don't have any contribution. Now let me try to do the same thing here. So this one, I need to hop from R to R plus Y. Now the path integral is like dy, and I need to pick up x component, bx. But as you can see, the x is fixed along here, right? X is not changing. So what I want to do is, okay, let me just write it. So I want to write this to discrete indices. Like, let me just call this m n. This side is m plus 1 n. This side is m n plus 1. Then this x is going to be m times a. So this is equal to b, and there is another a coming from right. We are integrating from here to here, and the length is a, so b a squared times m. And if you put it here with e over hc, like let's also do that, e over h bar c, and I already calculated this. This is going to be b a squared m. b a squared is flux. I can erase this h bar and put it like 2 pi here, and hc over e, like let's write it like this, hc over e is flux, ba square is total flux, so this is flux, this hc over a is flux quantum, and I can erase that. And I want to write it, I don't want to write phi over phi every time, I want to shorten it with 2 pi alpha m. Now let's write the Hamiltonian. In the first form we wrote, so h is equal to minus t. So this is mn. So c m plus 1 and dagger c m n. So this is the hopping in the x direction, plus now I have this spiral phase, e to the I, 2 pi alpha m, c m n plus 1. I'm hopping along the y direction, and c mn plus Hermitian conjugate. Good. So you can see now we replace x with m symbol and y with n symbol, and for a given n, for a given y, there's still translational invariance along n direction or y direction. Right? There's like, if you go in along y for a given fixed y, there is no y dependence here, right? Because there's only m dependence. So then y translational invariance is still intact.
I don't get this one. I mean, when we translate across y, we are increasing or decreasing
Mhm.
the m number.
Yes.
So, each time we are adding some phase.
Yes. I mean, but the phase comes from m dependence, right? So a Hamiltonian H is breaks translational invariance if there is anything with x dependence, right? If you only have, like, for example, px square over 2m, this is translationally invariant. But whenever you add something with x dependence, like for example this harmonic oscillator, you just break translational invariance along this direction. I look at this Hamiltonian, and whenever I hop along n, right? Whenever I go along n, there is no n dependence, right? There is no y dependence, but there is an m dependence here because the Peierls phase you pick up changes from one m to another m, and that's why we need to take into account this. Like this y is broken. X translation invariance is broken. So let me introduce translation operators and see if we get what we obtained on Monday. So translation ops. I'll introduce tx, one translation along x direction, and ty, one translation along y direction. And this is going to be, let me write it in the second form because this is a little easier to calculate, at least for this case. So this is m plus 1 n mn. So what this does is like takes you from mn and puts you m plus 1. And ty is equal to mn, the same thing, mn plus 1 mn. So if we didn't have any Peierl phases, this would be the end. But when you hop in n direction, you can see this term is taking you from n and hopping you n plus 1. You need to pick up an additional phase. So here I need to put e to the I 2 pi alpha m. And here you need to remember this m comes from x coordinate. X coordinate is equal to m times a. And we generally take a to be 1, but sometimes we can preserve it if it is needed. So tx, ty is equal to, let's just write this. Like that. So the second one I'm going to put primes. And so this thing is going to give you delta m prime, delta n prime plus 1, or another way to say this, n prime is equal to n minus 1. And this one is going to, okay, there's also n prime summation here. So the end result is m plus 1 n. So this one is gone. M prime is equal to m. N prime is equal to n minus 1. And let me shift it just a little bit. And this is e to the I 2 pi alpha, m is equal to m here. So this is tx ty. And we also need to calculate ty tx, right? And big deal we considered on Monday was like these two things were not equal. So tx ty, I want to do ty tx. So like this. Put this in. Let me just lift it like that for a minute. So this one is here. So which one did I put? So I think the prime ones I like to put in that one, and this one is also prime. Let me just put this here. Now I can erase that. Did I get it? Tx, ty, tx. Okay, good. So, and this one is going to give delta m prime m plus 1 delta n prime n. So there is also m prime and n prime summations here, and this is going to be equal to m n e to the I 2 pi alpha. M prime is, you can see, m plus 1 m, and the plus 1 I want to write it in the front, e to the I 2 pi alpha, and this is m prime is m plus 1, n prime is n, so this is n plus 1, and this one is m n. So here you can see this is like a summation, right? You are summing over everything. You can just define this one to be n tilde, then this one is going to be n tilde plus 1. Now this is n plus 1, n tilde plus 1, n plus 1, n plus 1, and n tilde is like a dummy variable. Once you change the variable, you can drop the tilde, and the only difference between this line and this line is this additional phase, right? And that's exactly what we found on Monday, like tx, ty was commuting up to a phase. Excuse me, to the I 2 pi alpha ty tx.
Minus
Is it? But here I'm just saying, like, I'm just comparing this line tx ty. This is m n m n, and I'm comparing with ty t. Like, and this term is exactly equal to this term.
Yes. Exactly.
Oh, I see. Yes. Then you are saying that, yeah, it has to be the other way. Yes. You are saying this. Pull it on the other side, right? Yes. Yeah. If you multiply it, yes. I got it. Yes. So this is the first thing we showed. Now, if we have translational invariance along y direction, why don't we take Fourier transform, right? So translational invariance along y, then it suggests, like, take Fourier transform, and I will define the Fourier transform like this: Cm n 1 over the cells along y direction. I will put ny, and this one is going to be ky e to the I ky times n cm ky. Right? I just destroyed n and then replace it with momentum index. So if you plug this in to this Hamiltonian, okay, this one, let me just copy. I think at some point when you work with these things, you don't need to take Fourier transform because you know which term gives what, so you can just write it, and that's what I'll do. And I'll try to motivate you. So this is going to be equal to minus t. So we are taking the translational invariance into account along n direction. So this is going to be, there will be only m dependence, and n dependence will be replaced with ky. So this thing is going to be cm plus 1 ky. You can see ky is diagonal here, and so this is the same thing, but this one is m, and this is dagger. So this thing here, you can see this is n plus 1 n. So this is going to bring up a e ky term, and it is going to combine with this. But the Hermitian conjugate is going to bring e to the minus I form. So these two things are going to combine and give you 2 cosine ky plus 2 pi alpha m cm ky dagger cm ky. Good.
Just leave the Hermitian conjugate for the first time.
I think yes. So what I can do is like if I do it like 2t, because they are the same, now they should be equal, right? Yes. Yeah, in my notes I also missed that, but never mind. So now we can convert from this form to like the third form, like in the tight binding model. If you remember, we have this, which is the one I prefer because this can be generalized to many body cases without anything. This one is a little bit easier to work with for those who are coming from quantum mechanics, and this one is a little bit useful for numerics. And let me try to derive this form by looking at the Hamiltonian. So this is going to be, okay, you can see minus 2t, there are two terms. I will have a psi m plus 1. Let me not write ky, not to clutter it, but there's also ky here, plus psi m minus 1. So this is going to give that. And the second one is going to give minus 2t cosine ky plus 2 pi alpha m psi m is going to be equal to e psi m. And this one is what sometimes people call Harper's equation. This flux here, which we'll talk in a little bit, can be chosen if you want periodicity or not. Actually, let me talk about this now. So this Hamiltonian is translationally invariant. So let me just ask you, is it, or what is needed? What is needed to get translational invariance along M? Right. So the first term there is no problem, right? I only need to take into account the second term. And for translational invariance, what I need is like cosine.
You always need one.
I missed one.
No. You always need one for cosine. You can I mean, ky plus 2 pi alpha m is going to be 2 pi's or something like that.
Oh yes, that's what I'm trying to show. Yes, m goes to m plus 1, right? That's what I want to do. So this is ky plus 2 pi alpha m plus 1, but nobody tells me to get like one unit cell, right? Maybe I can go like 1 unit cell, there is no translational invariance. If I go 2 unit cells, that's maybe the case. Maybe it is like 3 unit cells. So the most general thing I can do is like here I can say maybe if I go q unit cells, I'll come back to myself. And for this to happen, you are going to find if okay, this is equal to this. If this condition is satisfied, then I have to have alpha should be 1 over q. Then cosines are equal, but nobody tells me to get like it is like 2 pi cosine x is equal to cosine x plus 2 pi. But I can also say like p times cosine, right? I can also transform cosine p times, and these two are supposed to be integers, and if we also choose P and Q to be coprime, then we have translational invariance along x direction. So the result is Q cell periodicity along along x direction. Good. Okay, we have time. Now what I want to do is I want to write this Hamiltonian, and then hopefully I want to show you some nice pictures, and then we can finish it there. So what we need to do, I mean, either one is fine. I will work with this one. You can see this one is like I'm going to write it in Q cell basis. We need to form Q by Q Hamiltonians, and in that case diagonals are going to be filled with these cosines, and one of diagonals are going to be filled with these minus 2t's. I think when we write it like this, you see psi m plus 1n, I don't think I need 2 here, because it is taking care here. But 2 here is necessary. So let me try to write this. So this is 1, 2, 3, dot, 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 q minus 1, maybe. Let me start from 0. So 0, 1, 2. So 0, 1, 2, q minus 2, q minus 1. So this one is 0, 1, 2, q minus 2, q minus 1. So q by q matrix. So the first one is cosine ky plus 2 pi p over q times 0. And the second diagonal is, let me just fill up the diagonals. The second diagonal is going to be 1, and all the way up to, for example, this one is going to be q minus 2, and this one is going to be q minus 1. Right? If you put one more q, you come back to yourself. Also, what I did is like I want to absorb this minus t to here. So let me not write minus everywhere. So now this is 2, like this. So I have taken the diagonals. Now I want to put the off diagonals. So this is going to be 1, 1, 1. This is going to be 1, 1, 1, and so on. Right? So that's the matrix. And now I need to take one more thing. Like if I go from q to q minus 1 and go one more time, I need to come back to myself. And here is the Bloch condition. Let me first remind you Bloch condition. Psi x plus a. So this is the general. Now I'm going to generalize it to like this q form. It was e to the I ka psi k of x. So this is the usual Bloch form. Here we need to psi m plus q. If I go q times, I should come back to myself psi m, but up to a phase e to the I q I kx times qa, right? So what I did is like, so a here is one lattice constant, but in this case we have q times a. The unit cell size is q times a. Here wave vector was k, here it is kx, the momentum along x direction, because I now have x and y directions. So what I will put here is e to the, so this one is going to be e to the minus I kx q times a, but we take a to be 1, so let me just write it like this. And this one is going to be e to the I kx times q. And Brillouin zone is like kx is going to be defined inside minus pi over qa to pi over qa, whereas ky is going to be defined in minus pi over a to pi over a. So this is my Brillouin zone, and it is not equal in x and y directions. So the picture is something like that. So I have like these one-dimensional unit cells, and I divide it into q pieces. Dot dot dot. And each one has like a alpha p over q flux. So this is q is equal to 0, 1, 2, dot dot dot, q minus 1. And that's why the Brillouin zone size in that, okay, this is real space. In the reciprocal space, this will give ky pi over a. This one is going to give pi over qa. Okay, so let me show you some pictures. So what I want to do is like, so this matrix, you can see this is a gigantic matrix if p and q is, for example, q is large. But I will start from small and then show you a couple of examples how this plays out. I had somewhere here.
But this only works if p and q are mutually prime, right?
Yes, yes, absolutely.
But how do we implement it on a software?
So in the software, typically what you choose is like, so you want to choose. You can see like if p over q, if this alpha goes from 0 to 1, you come back to yourself, right? So we called it alpha in between 0 and 1. It's actually symmetric between 0 and 1/2. And for any number between 0 and 1/2, you choose closest coprime, right? And there's like software for this. Suppose like, I don't know, 0.3, and you can ask Mathematica to find closest coprime, and it's going to be 3 over 10, for example. But if it is like something like this, it's going to be 31 by 100. Right? In this case, you have to solve 100 by 100 matrices. In this case, you have to solve 10 by 10 matrices. That's why if you want really find resolution in alpha, I think that's a very good point. If you need a very fine resolution, you need to go to very, very large matrices, because some numbers will require really large coprimes. But for any floating number, Mathematica can find, or any software can find closest coprime. But typically, I don't do that. What I do is like, because this is not necessary, and that's what many people do. So you choose q to be 100, and I will show you pathologies with this. And you choose all p's. P is equal to 1 to 100. Right? You fix q and you choose each p. Then alpha will be scanned between 1 over 100 all the way to 100 over 100. But this is going to lose the periodicity, and you are going to have like some pathologies in the spectrum. I'll show you in a little bit. Like this, because if the periodicity is not satisfied, you are going to find these localized states in the gap. So if you are not careful. So this is a little bit too much detail, so you don't have to worry about it unless you work with this for your research. So here, let me just start with, let's choose 2 pi phi over phi naught to be, or this is p over q is equal to 1 over 2. And Brillouin zone will be kx pi over 2 to pi over 2, and ky is going to be minus pi to pi. To save time, I wrote the code here. I mean, if you ask ChatGPT, it just gives you the code in any language. But the point is, you need to sit down and try to understand it. Here is the one for one half placket. Anyways, like, let me just work it like that. So this is like 2 by 2. If I have 0 here, this is going to be ky, and the second one is 2 pi 1/2 times 1 is going to be pi, but cosine ky plus pi is going to be minus cosine. That's why you have like a minus here. And in the off diagonals you have this 1 and 1, and in these like from this block condition you have this e to the I kx and e to the minus I kx. And you can ask Mathematica to find eigenvalues. It's going to split something out, but you need to work with it a little bit because it's not sorting sometimes. And these are like actually they can be calculated with hand, and what you find is something like this. Let me try to run it and see if, let me see if it works here. Oh yeah, it works, good. So for 2D case, you can see that you have two bands and you have these so-called Dirac points. So these are what we called Dirac points. So two bands are touching each other and it's like a linear dispersion there. As an exercise, if you want, if you're interested, homework, linearize, because the equations are there, the spectrum, and show H is some form like V Fermi times P dot sigma form. Right? And you need to find what V Fermi is in the present problem.
But when we change the sign of this cosine, I mean, does it break the translation invariance?
Yes, right. That's why we have like not one cell, but we have two cells. So here you have two cells, and this is m is equal to 0. This is m is equal to 1. If you go from here to here, your cosine is going to be minus, but if you go 2 times, that minus minus is going to be plus. Right? That's the idea. That's why in these diagonals, here 1 comes with plus. If you go one cell, it is minus. If you go one cell, you come back to yourself. That's why we had to add these like periodic boundaries on the like these corners of the matrix. So let me show the second one. Let's choose. Okay, what's that? Okay. Choose 2 pi phi over phi naught to be equal to pi over 3. In that case, p over q is going to be 1 over 3. Right? In that case, p is 1, q is 3. You could also choose p is 2 and q is 3, and it's going to be exactly equivalent. Okay, maybe I can give you exercise. Show p goes to 2 and q goes to 3 is exact equivalent. And in that case, here I think I have it. So this is a little bit bigger matrix. You can see this is like cosine. Because of pi over 2, Mathematica, I didn't convert this. Mathematica automatically simplifies it. And this one also turned into sine, but you can see I put as an input 2 pi over 3 times 0, 2 pi over 3 times 1, and 2 pi over 3 times 2. And these off diagonals are 1, 1, 1, 1. And the corners of the matrix is I times 3kx, I times 3kx, and I times plus 3kx. And isolating these bands were a little bit difficult, but again, if you ask ChatGPT nicely, so this is like generated there, and you have these 3 bands. So kx, ky, you can look at the boundaries, but this one is, so this is first band, this is second band, and this is third. And the difference between this one and the previous one, you can see like this one is gapless. The valence and conduction band, they are touching each other at one point, but these are gapped. And we'll see later, this is going to be key to understand some topological structure here. For example, here we cannot define topology because we need isolated bands for that, like for Berry phase and stuff. but here we can, and we can find these bands are distinguished by their topological character. So I think I have a couple of more pictures. So there's also like you can do this for general PQ. For example, here what did I do is like I think I defined some large Q, and I did exactly what I told you. Like you can see, like there's some Q max defined to be 50, and that worked fine for me. You can make it bigger if you want, and you scan all possible co-primes. And in that case, for each alpha, you find the spectrum and you put one dot for each energy. But this is the pathology I was talking to you about. So let's copy this. Nicer. So you can see 1/2, we found two bands and they were touching each other. Like here, for example. Like there was like one full band like this and another full band like this. But this simple-minded picture neglected that. And there's another one here, one band here, another band here, another band here. So for that, you need to like think about these bands one by one, right? There is like, where is the band minimum and where is the band maximum? Generally, band minima are going to be like at the center, and band maximas are going to be corners of the Brillouin zone. So you can calculate eigenvalues for two things, these 2 points, and you can put a line between these two energies. That's what people generally do. Manually, they just draw these lines like here, and here, like I said. So there is one more thing. Let me give you as a homework because we are running out of time. So homework. Let's consider the continuum limit. Consider continuum limit. So what this means is like this, for example, I think at least for this exercise, I like to work with this guy. So start from here, and in the continuum limit, what you are going to do is like, for example, this psi m plus 1 means psi x plus a, and you are going to do Taylor expansion psi of x plus a times psi prime of x plus 1/2 a squared psi double prime of x. So this is the second derivative. And you are also going to expand, so this is the expansion of this term. You are also going to expand cosine ky plus 2 pi. Let me write it like phi over, let me write alpha, I'll fix it later if I need to. So this is alpha m is going to be 2 minus ky plus 2 pi alpha m squared. And you can see here, there is like the first term, like this guy will cancel. There is like something like minus, let me write it like some coefficient a times the x squared psi, the x squared, plus b times ky plus x, let me write it like this, x squared is equal to h, right? So let me write it h tilde. So, and what is this Hamiltonian? Hopefully everybody remembers what this Hamiltonian is. There are like some coefficients, like second derivative, and there's like x squared, but x squared is shifted. Exactly, right? This is harmonic oscillator, and this is exactly what we get for Landau gauge. This is the Landau gauge. Landau gauge harmonic oscillator. And from here, okay, you find A and B, and also you write spectrum immediately, right? H bar omega n plus a half. You also find what omega is, right? This is a little bit in disguise. And once you do that, you know these lambda levels are going to be linear, right? This one, for example, so there's like, for example, this is the first lambda level. This is E is proportional to h bar omega, or because h bar omega has B, so there's like flux inside and there's B inside. So this B, okay, let me call it beta, this is another B. So this is going to be proportional to B. The second one is going to be proportional to 2B. The third one is going to be proportional to 3B, and so on, right? These lambda levels like that. And this is exactly what you see here. So this is like a linear, okay, let me use red. So there's like a linear here, another linear spectrum here, another one here, and another one here. But you need to find these fitting coefficients. I had it here, but I think I ran out of time. If you are interested, we can talk about it. Okay, thank you.